We've done 20 videos.
This will be number 20.
This is our 20th lecture. This is our first lecture back from spring break. I'm glad to see all of you here that are here. On Wednesday, the last time we had class, we took an exam. And so I have those exams ready. And I want to tell you that I was real disappointed that class was canceled on Friday. I mean, you may not be disappointed, but I was. And I'm going to tell you why in this very quick when we get to work. The reason was is that, number one, I graded your papers for Friday. So I was ready to pass them back. And so nobody knows. I'm telling you, you don't have to believe me, but I did it, you know. And so nobody got to see that I did it. So that didn't make me feel good. And then secondly, I live 80 miles away from campus. And the weather was awful. But the university did not close, or announce it was closed till around 6:20 on Friday. For me to have gotten here to teach my 9 o'clock class, I didn't feel comfortable waiting until 6:20. So I left my apartment much earlier than that and was driving here and got here to find out that the school was closed, which was okay with me because I got a lot of work done on that Friday. So everything was fine. I'm not upset or anything like that. Everything was good. But that's just what happened. But I had your papers ready. Okay, look, papers weren't beautiful. Okay, they were not. And so here's what I'm going to tell you. This is test 1 distribution. And then I'm going to say this is the current course averages. Well, I say course averages, but really what I'm going to do is just list the number of A's, B's, so A's, B's, C's, D's, and F's. Okay, so I'm about to write these up. I know you're anxious to see what they are. I'm going to tell you that we had 2 A's on the test. We had 2 B's. We had 2 C's. We had 1 D, and we had 5 F's. And then the course averages right now, there would be 3 A's. There would be 2 B's. There would be 3 C's. There would be 3 D's, and there would be 1 F. That's the grades that would be given at this point. Okay. I'd like to pass back your papers at this point. If you have questions about something, you let me know. If there's something I can do that would help you to do better, you let me know. One of the things that I think should be done is what I'm going to do. So this is something to, I think, pay attention to. I'm going to institute the following grade policy. If you do better on your final exam in your lowest grade material, I will replace your lowest grade material by what you did percentage-wise in the final. So let's say you made a 53 on this exam. I don't know if anybody made a 53. It's been since Thursday since I looked at the test. Okay? So I don't remember anybody's grades. But let's say you made a 53. And let's say on the final exam you make 81%. And if 53 is your worst score, then I will replace it by 81. I will replace whatever helps you most by 81. Does that make sense? Final exam counts, okay? And the reason I can do this is because the final exam is comprehensive. So we've got to learn this material to move forward. Okay. Okay. So you make sure I added the points correctly. If you have any questions, you let me know. This is what I saw. Nate. John. Cal. Adam's not here. Audra. Corey's not here. Chuck is here. And Melissa's here. So what you should see is that you see your grade on the test out of 100. It was originally out of 96 or 96 points. And then somewhere on that first page, I also tell you what your course average is at this point. Okay? So somewhere on this, I'll tell you that. Okay, let me give everybody just a second to look through it. You make sure I added the points correct. If I made a mistake in adding, maybe just show me. That's what, and I verify. If I verify that that's correct, it's been a mistake. We make the change. That's what liquid paper is for, to make adjustments when people make mistakes. So if there's anything like that, you just let me know. If you have questions about the way something's graded, you let me know. If you want to see how something's done, I'll do it. We're just going to give everybody a few minutes. Does anybody want to see anything done? Yes, sir. Number 5. Yes, sir. Okay, so on this one, it had to do with, I think, about an MTEL sequence. All right. Thank you very much, Doctor. So, listen, there were people who took the exam at the regular time and people who didn't. They took it in class and people who didn't. So I gave 2 different exams. So I'm about to do number 5 for the people who took the exam in class. You took the exam? Yeah. Okay. So here's what it was. So this is 5 from test 1. And here we're having X of n is a sequence. And its formula, so not every sequence can be given by formula, but this one is 2n times, or over 5n plus 1. N runs from 1 to infinity. And so we're supposed to give a formula for the 4th tail sequence. Okay. So Dalvin and everybody else in there, the 4th tail sequence would be x of 4 plus m, or let's say n, is n runs from 1 to infinity. So that's what it is, the 4th tail sequence. I haven't written down the formula that I'm looking for. That wouldn't be the right answer, okay? But that's part of the work to get to that answer. Dalvin, do you have something that you're thinking about before I go any further? Okay, let me take a look at yours. Okay, so Dalvin, all right, wonderful. Let me write down that you had a different one. That's right. Everybody who took the one in class got a different one. I did the one that was taken outside of class. So let me make that change. Thank you very much. I'm sorry. Okay. Good, Alvin. Thank you. So here's what the formula was. It was 3 to the n minus 4 over the n. Okay? And it doesn't say find the 4th tail. It says find the 8th tail. And so here the answer for the 8th tail is this formula. Okay? 8 plus 9. And so here's what we think about it. We're replacing the n's involved in our formula with the quantity 8 plus n. Is that okay? So here's the answer. It's equal to 3 to the 8 plus n minus 4 over 8 plus n as n runs from 1 to 50. That's all. So that's the answer. Dalvin, thank you very much for asking. No, that's okay what I've written on the board. Anybody else? Or any other questions from the test? Any other problems anybody like to see done? One last call. Any other problems that people like? True, false? Anything? Of course, we know the answer for the true, false, because if you got it right, that was the answer. If you didn't, it was the other answer. You may say, wait a minute, I don't understand how come this is the other answer. You can ask. Last problem was something done by induction. Okay. Well, if there are no other questions, then I'll move on. And if you think of something else you'd like to ask about for the test, feel free to ask me outside of class. No worries. You can always come back and ask something. No problem. Well, we ended last time, I believe, so I'm saying this, but it's also a question too. Okay? Just to make sure where we are. We ended last time with the monotone convergence theorem. I think that's the last thing that we did. So we talked about what it meant to be a monotone sequence. We talked about what the monotone convergence theorem was. It was an if and only if statement having to do with a monotone sequence would converge. Okay? It converges if and only if it is bounded. That's the answer. Okay. Today we're switching topics, not from sequences, but from certain things within sequences. And so we're going to start off with the topic today is subsequences. So what is a subsequence, or definition? So given a sequence x of n, and I'm not writing this down, Chuck, but when we're looking at a sequence x of n, it's a sequence of real numbers. That's exactly right. So I'm just being a little careless here with my definition. That's what we're talking about. Given a sequence x of n, and John, a sequence, I'm going to say this, a strictly increasing sequence. Of natural numbers. So, Megan, here's my natural numbers. It's n sub 1 less than n sub 2, less than n sub 3, less than n sub k, less than, goes on forever. Okay. Then, x of n sub k, as k runs from 1 to infinity, Melissa, is called a subsequence of x of n. So that's what a subsequence is. That's the way we define it. We need to look at the idea, maybe, and examples here.
Picking and choosing some of the terms.
Yes, we are, with one other little caveat, and that is we want to keep the same ordering, if you will. And that's what this part right here, the increasing sequence does. So let's look at the idea. So I'm going to say the idea, what I think of the idea of the subsequence. Okay. So the idea is one, each term of the subsequence is a term in the original sequence and a subsequence preserves the order, I'll say ordering of the terms. And so I'm just going to put that in quotes because maybe that's not so clear what I mean, and I'll try to illustrate that through examples. So Megan and I'm going to look at my favorite example of the sequence. And over here on the board, Melissa, I've got the original sequence from which we're getting the subsequence. But Audra, sometimes I'll call that original sequence the parent sequence. And so, John, what I mean by the parent sequence is the sequence from which a subsequence might be derived. And I'll call it the parent sequence because, in general, not everything maybe, but most things that are characteristics of the original sequence are inherited by the subsequence. Okay? Not all, but lots are. Okay? Lots of things are inherited. So, okay, let's look at examples. So I'm going to look at my favorite sequence. So we're going to consider x of n, this original sequence, is equal to 1 over n. Dalvin, I know about this guy. What's the first term, Dalvin? 1. What's the next term?
1/2.
That's right. 1/3, 1/4. How about this one? 1/5. I'm not tired. I'm going to keep going. 1/6, 1/7, 1/8. It keeps going. Okay. Then, if you look at this sequence, let's say 1/2, 1/4, 1/6, 1/8, and so forth. That's really equal to 1 over 2n, where n runs from 1 to infinity, is a subsequence of 1 over n. So I'm going to check these two qualities I got listed above. Just a second, give everybody a second to write it down. Okay. So, John, this is a subsequence. Why? Every term in what I'm claiming to be a subsequence is a term in the original sequence. 1/2, 1/4, 1/6, 1/8, 1/10, 1/12. They're all part of the original sequence 1 over n. Is that okay? Each one is listed. Not only that, but they preserve order. Here's what I mean by preserving order. 1/2 is the first thing I've got listed. Everything that follows 1/2 is also things that are follow 1/2 in the original sequence. Okay? And the same thing for 1/4. Everything that follows 1/4 is something that follows in the subsequence. They follow in the original sequence. Is that okay? There isn't a jumbling of it, as opposed to what I'm about to write. So I'm still working kind of within the same example. So Audrey, let me show you something that's not a sequence, not a subsequence. This is it, not a subsequence. But here I'm going to say 1/2, 1/4, 1/8, 1/6, 1/16. 1/14, 1/12, 1/10, and going on in this fashion, is not a subsequence. Of 1 over n. You say, what do you mean it's not a subsequence? Hold on. Every term in here is a term in the original sequence. Yes, but that isn't preserving order. See, here's what's happening. Look, 1/8 is followed by 1/6. But in the original sequence, which comes first? 1/8 and 1/6? 1/6. That's wrong for it to be a subsequence. Is that okay with everybody? That's valid. Okay? Okay. And the following sequence right here, if I write down 2/3, 3/5, 4/7 is not a subsequence. Of 1 over n. The problem is that 2/3 isn't a term in the original sequence. Is that okay? So it doesn't contain terms from the original sequence. So those are things to keep in mind when we're talking about subsequence. It's got to preserve order, and You're pulling terms from the original sequence. In the same way. Okay. So if you look at a subsequence of a sequence, what properties does it inherit? What can be said? So let's think about this. Well, before I get into that, let me prove some fact having to do with the definition that comes from the definition of a subsequence, or that's involved in the definition of subsequence. Here's a fact. If n sub k is a strictly increasing sequence of natural numbers, then n sub k is going to be greater than or equal to k for all k element natural numbers. I want to prove this fact. And we look at an example, see if it's holding true for the example. Maybe get a little bit more experience working with this definition. Subsequences as well. Okay.
Induction.
Yes, that's right. Good. Thank you very much. Proof is by induction. Yes, so John, that's a good comment. The reason the comment makes sense to me is because we're trying to prove a statement that has to do with each natural number. Okay, for every k, for all k element, and induction is a good way of doing that. So here, we're doing the induction on k. Okay, here's what I'm going to say. So when k is equal to 1, okay, what we're trying to show is that n sub 1 is greater than or equal to 1. So n sub 1, n sub k, is greater than or equal to k. Okay, so I wanted to say we need to show this. I wrote down something too quick. We want to show that's what we want to show. Well, since n sub 1 is a natural number, then automatically, you give me a natural number, it's got to be greater than or equal to 1. So the statement is true for when k is equal to 1. Okay, so now we've got to assume it's true for a general k, and then show that it's true for the next number. So I'm going to say, suppose, normally we do induction on n, but here we're doing induction on k. So I'm going to say, suppose the statement is true for k equal to j. We want to show, all right, let's say that something. That is, we got n sub j is bigger than or equal to j. So this is an arbitrary natural number j, but we're thinking it's fixed. We want to show I'm going to write a little bigger here than I normally do. This is going to have some indices here to worry about. We want to show that n sub j plus 1 is greater than or equal to j plus 1. That's right. That's what I want to show. That's what we want to show. I haven't shown it. We need to show that. You know, it's kind of important to know what is it that you need to do to accomplish the goal. So that's what it is. Okay. All right, well, here's what I think. Since n sub k is a strictly increasing sequence of magnitudes, then how does n sub j plus 1 compare to n sub j? Which one's bigger? That's right, the n sub j plus 1 is bigger. So I'll say it's bigger, strictly bigger. That's what we have. Is that okay with everybody? Okay. So that means that n sub j plus 1 is going to be bigger than, now both of these are natural numbers, is bigger than or equal to n sub j plus 1 in this fashion. It's not n sub quantity j plus 1. It's n sub j, that number, plus 1. That's what I got over on the inside. Why is that? Hey, look, you give me two natural numbers. This one, the one on the left is bigger than the one on the right. Okay? They are going to be separated by at least 1 unit. Is that okay? The closest they could be together is within 1 unit. So if I add 1 to the smaller one, I might get up to the bigger one. Might. But I sure didn't pass it. Is that okay? So that's what's being said there. Okay. Okay, well, note, n sub j is bigger than or equal to j by assumption. But from that, we have that n sub j plus 1 is definitely bigger than or equal to j plus 1. So look, these two guys, we have n sub j is bigger than or equal to j. So I'm adding 1 to both sides so it retains the inequality. Thus, we have, so if I put that inequality that I just wrote along with another inequality that we had on the board, here's what we see. N sub j plus 1, I'm looking down here, is greater than or equal to n sub j plus 1, that's what's written down there, but that part is greater than or equal to j plus 1. So if you take out the middle term, n sub j plus 1, here's what you have. And that proves it. Thus, by induction, we have n sub k is always greater than or equal. That's that theorem. That theorem is going to be important. That fact is going to be important to us. Because of the following. We've got a theorem talking about inheritance then. So if x sub n is a sequence of real numbers, then that converges to x, then any subsequence, let's call it x sub n sub k, here k runs, converges to x. Now that's what we're going to prove. We got it written down. But actually, I'd like to take a step back. I wrote down this theorem, and that is what we're going to do next, almost. Except, what did we just prove? That fact. It proved that the indices of a subsequence is bigger than the indice of the regular sequence in terms of their positioning. So here's what I mean by that previous fact. I want to do an example of this. Okay, so before I prove this theorem, okay, I'm sorry. I know this is a little bit disorganized in that I forgot to do this illustration. So here, just as parentheses, if we have the sequence x of n equaling to 1 over n, remember that 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. This is the first term of the sequence. This is the second, third, fourth, fifth, sixth, seventh. Okay. And underneath it, what I'm going to look at is I'm going to look at x of n of sub k, where k runs from 1 to infinity, equal to 1 over 2k, where k runs from 1 to infinity. Here, these terms are 1/2, 1/3, 1/4, 1/6, 1/8, 1/10, 1/12, 1/14, don't stop. Okay, this is its position. Okay. This can be written x of n sub 1. Okay? X of n sub 1 is equal to 1/2. Is that okay with everybody? It's the first term of the subsequence. That's why the 1 is there. But it's also equal to x sub 2 from the parent sequence. Is that okay? It's the second term. It's x sub 2. Is that okay? And so here's what I'm saying. This means n sub 1, now look, so we get very clear. N sub 1 right here is equal to, n sub 1 is equal to 2. Okay? And 2 is greater than or equal to 1. There's the k, the n sub 2, or n sub 1 is 2, but it's greater than or equal to 1. Is that okay? The number that is n sub 1 is bigger than 1. Is that okay? And that's what we're kind of matching up. That's what that previous fact said. So I'm sorry that I had listed something before I had done this illustration. One thing to get out of this is the following. If you go to the 4th spot in this sequence, okay, you get the number 1, 4. Okay. If you go to the 4th spot in this sequence, you get the number 1, 8. And so the 4th spot beyond in the subsequence is a lot further along in the parent sequence. Is that okay? The output values. So that's something to keep in mind. All right. Well, we want to prove our theorem. What theorem we're talking about? That every subsequence of a convergent sequence converges to that number. Okay? So we're going to prove that. So here, we're going to let x of n converge to x. We're going to let, we want to show any subsequence will converge of x of n, will converge to x. I can't show it for each one of the subsequences specifically, so we have to do this in general. We just say, let x of n be, or x of n sub k be a subsequence. of x sub n. Okay, the index for the subsequence is k, that's what runs. The index of the original sequence is n. Let me remind myself what it is that I need to show. So let me write this down. We want to show that x sub n sub k, so k is the index, converges to x. Okay. I'm trying to show a sequence converges. Audra, they got the same format. What am I going to say?
No, that's not
Be given. Okay, that's what I'm going to. Okay. Well, I say they got the same format. But John, but Melissa, Chuck, Megan, we're not going to have the same need. We said we need a K, right? That's what we normally say. But K is the index. It's like the N in previous problem. So I'm going to just use a different letter. I'm going to say we need a J. There's an element of natural numbers. Such that for all K bigger than or equal to J, here I'm going to write something. Absolute value of what? The sequence I'm talking about. How do I describe the sequence I'm talking about?
X sub n sub k.
Minus
X.
is less, inside absolute values, is less than. That's what I want. So I want this. I don't have this. Is that okay? Okay, so here's what we have. Since x sub n, what do I know about x sub n? Chuck?
It's no natural numbers. Wait. It converges.
Okay, it converges. What's it converge to?
X.
X. Since this converges to x, we've been given an epsilon. There does exist this j. I don't know if this is the j I'm looking for, but there exists this j among the natural numbers, such that for all n bigger than or equal to j, absolute value of x sub n minus x is less than epsilon. Okay, I got a little space here. I want to use it. Now, what I want to note, I could re-say this, for all k bigger than or equal to j, x sub k minus x inside absolute values is less than epsilon. I just said it that way just so I could get things in terms of k, but it wasn't so important. I'm writing the same thing with different letters. It's not so important. Okay. Now, since that fact we proved, n sub k is bigger than or equal to k, then for all k bigger than or equal to j, well, if k is bigger than or equal to j, then n sub k is bigger than or equal to j. Stop it for a second. Give everybody a second. Okay. What I want to do, that's right. So for all k bigger than or equal to j, n sub k is equal to j. What is j? What's so big about j? Let me come over here to the back. at previous board. What's so big about J? J is this guy. J is a spot in the term of the original sequence, such that if the index of the original sequence is bigger than J, the term in that spot, distance from X, is less than epsilon. And that's true for all terms who's bigger than or equal to J. So, as long as this written right here, this guy, this is sub-index, is bigger than J, X of that sub-index, whatever that sub-index is distance from X is less than epsilon. So as long as this guy is bigger than or equal to J, we get this result. Now, come back here. For all K, bigger than or equal to J, well, N sub K will be bigger than or equal to J. So N sub K is an index. So X sub N sub K, and the index here is N sub K, and it's bigger than J, then the term in that spot is distance from X is going to be less than epsilon. That's what it says. Thus, this subsequence, X sub N sub K, as K runs from 1 to infinity, converges to X. Okay, so here in a very quick summary, that is the proof. Kind of the idea is what I said through that example that we did, or can be seen through that example that I did right before the proof. Okay? Is that if you look at the parent sequence and you go to a certain spot and say, hey, after that certain spot, all the terms of the sequence are really close to X, then epsilon means whatever that particular epsilon was. Then if you go to that same position in the subsequence, the terms in the subsequence are going to be terms from the original sequence, which happened later on in the sequence. So beyond J, is that okay? For which we know their distance is within epsilon units of X. So that's what we get. So that ends that proof. The next thing that I want to do is do a proof having to do with when a sequence doesn't converge. Okay? Sequence doesn't converge. So let me write up this theorem. So it's an it's a statement that has several parts to it saying that they're equivalent. So here's what it says. It says let X sub n, as n runs from 1 to infinity, be a sequence. Then the following are equivalent. One. So here's what's good. First thing is that X sub n, oh, I'm sorry. I made a mistake. I need to add something. Let X be an element of R. Then the following are equivalent. So X is some real number. So the first statement, 1, is the sequence X sub n does not converge to X. What is that equivalent? That's equivalent to the following statement. 2. there exists an epsilon naught greater than 0 such that for any k element of natural numbers, there exists an n sub k bigger than k, okay, where n sub k is an element of natural numbers. That's what I should say. N sub k is an element of natural numbers with n sub k being bigger than k, and the absolute value of x sub n sub k minus x is bigger than or equal to epsilon naught. And that's equivalent to the following statement. There exists an epsilon naught greater than 0 and a subsequence x sub n sub k, k runs from 1 to infinity, of x sub n, such that the absolute value of x sub n sub k minus x is going to be greater than or equal to epsilon naught. So that's the statement. These things are supposed to be equivalent to each other. We're going to prove that by showing 1 implies 2, 2 implies 3, and 3 implies 1. So there's this path that from any particular statement you can get to any of the other statements. Let me give everybody a second to write it down. Okay, I think we tried at least get started on 1. Here's the proof. We're going to show 1 implies 2. So we're going to let x of n be a sequence that does not converge to x. And what do we want to show? We want to show 2. That is, that there's some epsilon naught such that for any natural number you give me, there's another natural number bigger than the natural number that's given, such that x sub that natural number minus x is greater than, greater than x. So, so here's what I think from our assumption, that we have this sequence x of n that doesn't converge to x. Okay? What does it mean? It means the definition doesn't hold true for conversion. So it is not true So it is not true that for each epsilon greater than 0, there exists k element of natural numbers such that for all n bigger than or equal to k, x of n minus x is less than x. That's not true. So what does it mean for it not to be true for that? For every epsilon, the following happens. Well, that means that if it's not true, if you make a blanket statement for every epsilon, this has got to happen. You say, well, that's not true. To disprove that, there's got to be one epsilon. Does that make sense? At least one. So there exists an epsilon such that it is not true that there exists a k element of natural number such that for all n bigger than or equal to k, x of n minus x is less than epsilon. Okay? So what does that mean? So there exists an epsilon naught greater than 0. This should say greater than 0. And so what does it mean for it not to be true that there exists a K? What's the opposite of there exists one of these? That means that there doesn't exist one of these that happens. That means that for all K element natural numbers, it is not true that for all n bigger than or equal to K, x of n minus x is less than epsilon. Let me write down this one last statement and then we'll be done. So what that implies is the following. So, there exists an epsilon naught greater than 0, such that for each K element of natural numbers, there's some natural number bigger than it. I'll call it n sub K. And x of n sub K minus x is going to be bigger than or equal to epsilon naught. And that's 1 plus 2. That's part. We need to show 2 implies 3 and 3 implies 1. Okay? So that's what we'll do next time. I believe that's my time. As we end, pardon me, that's my time. As we end today, let me say this. Okay, I want to be very truthful. I know you're still writing on what's on the book. I want to be very truthful. Scores were not as good as what had been in the past for my previous times teaching this class. Sometimes you test one. They weren't. Okay. Maybe I didn't do as good a job. The material's the same. Okay? Maybe I didn't do as good a job. Here's what I want to say. To compensate for any type of things that I didn't do as well as I could have, what I would encourage you to do is please come by to see me. I think the more time that we get to spend with each other, the better off you're going to be in terms of learning material. So that's my opinion about things. So I can't hold you any longer. You know, this is my time with you, but you can come by and visit. I'm available more time than this. So if you want to come by, please do so. Thank you very much.